one where you had to pull a negative 1 out in order to get everything to work out the way that it did. And one of the things that we've done is try to increase the things that Mrs. LaRue says they have to have these skills when they get to calculus, so please at least let them see it. So what you'll notice is the problem that we did in class was much more difficult than the ones that you did in the homework. You know, it was a tweak to let us know we have to do this from time to time. We have to think, hey, if I pulled a negative out of this, then I could get something to go forward. It's just that kind of little extra thinking that I think put you a little over the top on that one. Because you were doing great with these yesterday. And then, like I said, a good place for us to stop was right here with D. Because this one is interesting. You know, it's a little different. And that is, we want the sine of x to equal the cosine of x. And if we attack this like some of the other problems, what we would do is try to figure out a way to get this to be either all sine or all cosine and see if we could go anywhere with it. But that's not the best way to go after this. With this problem, what we literally need to think is, we have had a time, we have experienced a time when sine equals cosine. When did that happen? Think about our special right triangles. When did that happen? That the sine of a function also equals the cosine. It is a 45, 45, 90. So when we get to this problem, instead of thinking algebraic things, you think right away, wait a minute, that's a 45-degree angle that does that, you know? Where we've got our 1, 1, and our square root of 2, so for the 45-degree angles, it doesn't matter if you're going to do cosine or sine, they're both going to be the square root of 2 over 2. They will. That's just what happens. So then I think, okay, but on top of that, they also have to have the same sign. Definitely first quadrant. Everything's positive there. Not second. Aha. Third quadrant would be the other place where this is going to work. So if I put my 45, 45, 90 in first quadrant, what angle is that in radians? Pi over 4. And if we put that in third quadrant, where's that? 5 pi over 4. Any chance, because I didn't finish up, any chance in fourth quadrant they're going to be the same? No, the signs would be different. So this one is really a unique problem. In fact, if you do solve this one algebraically, the way that you would do it is by squaring both sides and moving forward from there. The problem is, because you square sides, just like you learned in Algebra 2, whenever you raise something to an even power, there's a chance you're going to get extraneous solutions, false solutions. And you actually end up with 4 solutions to these problems, 2 of which don't even work. So this, when you look at it, you should think, gosh, there's got to be something really basic about this that I'm supposed to know so that I can go forward with this. Don't even think about the algebra. The difference, of course, is when we get to E. Make myself a little bit more room here for this one. Because we do see, hey, we've got cosine of x on both sides, so maybe if we move it all over, maybe there's something we could do with this algebraically. So we'll subtract that cosine of x. We have to think, because this has a squared term. Remember, those are for quadratics when we're working in algebra. So is there something we could pull out of both of those? Cosine of x. Let's take it out. Well, now we're just thinking steps away from the answers because we have that zero product property that says if this answer is 0, this could be 0, because 0 times anything will be 0, or this could be 0. So we set those equal to 0. And we think our way through them. Cosine of x equals 0. That sounds quadrantal to me. Whenever you get 0, 1, or negative 1, you should think that might be quadrantal. Where does the cosine of x equal 0? So at 0, where else? Pi over 2. So 0 radians and pi over 2. Then this little bugger over here, we'd add 1 and divide by 2. Cosine of x equals 1/2. What special triangle are we talking about? 30, 60, 90. So cosine has to equal 1 over 2. That would be adjacent over hypotenuse. Which of those angles are we talking about then? 60-degree angle. So we want our 60-degree angle, which is pi over 3. Obviously, first quadrant is going to work. It's positive 1/2 here. And then what other quadrant would we get a positive 1/2 for? Fourth quadrant. So think about our little pi over 3 here and give me the correct name using the x-axis as the initial side. Oh! Oops. Sorry, I should have thought about that before I just wrote down what was said. Yeah, we need pi over 2 and 3 pi over 2. Those two. Thank you. All right, F. I'm going to need more room for that problem. There's a lot going on there. Well, first thing to think of is, doesn't do me much good if there's both cosine and sine in my problem. Can I replace any of that with something I know about cosine? That is the tip-off right there. But that's sine squared. That's the tip-off. So I think about my Pythagorean identity. And the fact that if I just solve it for sine squared x, I'll have 1 minus cosine squared x, and then all of this will be cosine. That would be helpful. But in order for it to be helpful, again, I have to kind of see it all on one side and see what I have. So let's see, because this is negative on the right-hand side, I'd want to add that over to the other side to make sure that that's positive. Because it's just like when you're factoring, you kind of want to keep your first term positive. And then we'd have this plus 2 cosine x, and I am seriously going to run out of room. There's no way. So we've got the plus 2 cosine of x, and then we'd have to subtract 1 from both sides. That looks like that. Possibly factorable. We've got a trinomial here. And if you don't want to factor with the cosines in there, you could say, well, couldn't I just think of it this way? You know, take the cosine out for a second and just think y squared plus 2y plus 1 equals 0. That might be a perfect square binomial right there. Because if you square y, you get y squared, and if you square 1, you get 1 squared, which is 1. And if you take 1 times y and you double it, you get 2y. This is a perfect square trinomial that can be factored as a binomial squared. But now I would have to put the cosine back in. This is just kind of thinking step, you know, is, hey, I don't like that cosine in there. I'm just going to kind of take it out of the picture first, and then I'll substitute it back in. So this would be cosine of x plus 1 squared equals 0. Squared there, sure.
Okay, so up top we need the f. It has 2 plus 2 cosine x equals 1 minus cosine squared x. So wouldn't you subtract 1?
You could move everything over to the other side, but yeah, if you take 2 minus 1, that'll be 1 on this side. Because we had a positive 2 over here, and when we subtract the 1, that will give us a 1 over here. I should not try to squeeze it in. That's fine. But yeah, that's exactly what we're doing. So we're adding a cosine squared x to both sides. and then subtracting the 1 from each one. All right, how do you get rid of squaring something? Square root. Well, the good news is it's a 0, so it's just going to be cosine of x plus 1 equals 0. Didn't really do anything there, but now we don't have to worry about the squared piece. And now we would just subtract 1 and think, where is that cosine going to be negative 1? Pi, that's it? One answer for this one? Yep. One solution out here at negative 1, 0. There it is. So again, quadrantals, be thinking, hey, if it's 0, if it's 1, if it's negative 1, that's going to be a quadrantal angle that we have there. Now this next piece we're going to need graphing calculators for. So anybody forget graphing calculators? Or not? Oh, that's right. It just went kapooey. Anybody else realize they don't have graphic calculator? All right. So this is, we are going to solve a trig equation with a calculator, and here's the reason why. They're not special. 7/10. There's nothing special about that. We can't sit there and think, hey, that's 30, 60, 90, 45, 45, 90. So we really don't have a lot of choice. And it's saying find all the solutions to the equation, and then you see they're using the graphing feature. And that's because if we just use that inverse trig function, we're not going to see all the solutions. All the solutions. So if we want to see all the solutions, we really need to grab a graphing calculator and see how things are working here. So here's what we're going to do. We're going to use our very old, I mean, it's probably one of the first things you were taught in Algebra 2 for using the graphing calculator. We're just going to use y sub 1 and y sub 2 and the intersect feature to see where do these two hit each other. We do need it radians, exactly, yeah. Make sure we're in radians. Going into y sub 1 equals, and we're going to put in that cosine of x. And we're going to put in the 0.7. And pretty obviously we got to do some window work here. So, in the window, normal period for cosine would be 2 pi. But let's at least see some negatives and some positives. So let's do negative 2 pi to 2 pi. And we know negative 1 to 1 is typically the range, so maybe a negative 2 to 2, just to make sure we can see everything. So there's our 2 full periods there. And we can see, hey, there's going to be lots of solutions, you know, because this is going to continue to oscillate, and it's going to hit in 2 spots every time. So what we want to do is think, how far away from each other are those points? Well, let's try this first. Let's use Blinky, second trace. Number 5, intersect, just to get one of them. And let's get Blinky a little closer so Blinky knows which one. We'll do this one first. And hit enter 3 times. So Blinky says we're at about negative 0.795. Interesting. Second trace, let me get the positive one. That's still going to be number 5. But I've got Blinky over there closer to that one. Oh, look at that. So it gets me thinking maybe I'm going to be able to put plus or minus 0.795 plus something. Now, we have to know how far apart these points are going to be. And I look at the cosine of x and I realize, well, the period is 2 pi. So it makes me think maybe this point right here matches up with this one if I just subtract 2 pi from it. But sometimes I doubt things a little bit, so maybe I'd check it out and see. I'm going to find that intersection, and then I'm going to subtract 2 pi from this, and I'm going to see, does that really land at the right place? So second trace, number 5. Take Blinky a little while. I always think Blinky needs some elevator music for these long trips. All right about there, Blinky. Give me that one. And we have negative 5.487786. So let's see. Is 0.795 minus 2 pi that? It is 2 pi. So you suppose the other one would work too then? By just adding 2 pi? Yeah, that's the thing. You know, we kind of have to check it out. Look at the spacing. That should tell us. From here to here was 2 pi. What do we think about this one to this one? Is that also going to be 2 pi? If we don't believe it, we use Blinky and we make sure. Okay, Blinky, back to the other side. Second trace, number 5. We'll Blinky over there eventually. Because we want to see, is that one negative 0.795 plus 2 pi? Just to make sure. All right, Blinkster, you're getting close. 5.48, so the positive of this so do I even know it? We need to really add 2 pi. I don't know what's going to match up. But anyway, like I said, if you're doubting Thomas, then this is what we do. Plus that answer we just had there. Keep missing the negative. So we want to know, do these things match up? They do. So what we have to do is put plus or minus this plus 2 pi n, where n is the set of all integers, because it's about the spacing. We have an answer every 2 pi. Now, how can you know that without having to use the graphing calculator to find them all and check them all? Well, what you do is you'd say, it's cosine of x. There is no b value here for me to take 2 pi over b and see that there's some kind of change in this. It's just not there. The period is not going to change. So when I see the graph, I think, well, it's 2 pi. I mean, that's going to be the period. That's where that repeat is going to take place. But now b is a little different, and that's because we've got this whole squared business. And we're not going to put cosine squared x into the calculator. What we have to do is take the square root of both sides. But that, of course, means we're going to have plus or minus the square root of 0.4. And the calculator doesn't do the plus or minus in the graphing mode. It does have a plus or minus key on it. It just doesn't like using it in the graphing mode. So we're going to have to punch it in as a positive and as a negative. So we'll put cosine of x into like y sub 1. And then we'll put positive square root of 0.4 in as y sub 2. Plus and negative square root of 0.4. And we'll take a peek at that graph. Windows should still be okay with what we have there. Okay. So now we see we have additional spots there where we're going to have solutions. And let's check out the 2 that are closest to our y-axis here and see what those 2 are. So negative 0.886. Do we already know what the other one is because of symmetry? If you don't believe, again, you can always do second trace, number 5. But now I have other answers up here as well, because you've got another line down here. So I have this one right here, and I try to think, is there a relationship between this and this that might get me an answer? And this might be an answer. And that's because of the spacing here. We had 2 here, and now we have 2 here. Well, let's test one of them. I mean, it looks like this has been split into 2 sets, given that we did the plus or minus. So maybe if we just add 1 pi, we'll get another correct answer, or subtract 1 pi, we'll get a correct answer. So second trace, number 5, plus. Let's try out this one. So our y value there, (0.632). Oops, wrong one. Come on, Blakester. I need that one. It jumped up. It jumped up again, you little stinker. Ah, that's why. Jump her back down. There we go. Wanted to go to that top line again. So the question is, if I take the 0.886 and I subtract 1 pi, am I going to get this? And I do. So with this one, we can go by 1 pi instead of 2 pi because of the spacing. Now, I would much rather do this with the unit circle. Your book has you doing this with your graphing calculator here. On the unit circle, remember, we can go 1 pi if our angles line up in a perfect straight line when we're doing this. So the unit circle is another way to do this. But with this one, what we can do is we can just say, we're going to use the set of all x, and you wouldn't necessarily need the set notation, it's kind of overkill. But we've got our plus or minus 0.886 plus just 1 pi n this time. I'm actually going to include that in the set notation, where n is the set of all integers. And that again is because of that spacing. Like I said, some books do a really good job of this with the unit circle. I'm not particularly fond of the graphic calculator piece.
What about all the solutions that are past -0.886?
And that's what we're saying here with this pi n, where n is the set of all integers. The integers are going to be -3, -2, -1, 0, 1, 2, 3, and they go on forever in both directions. So that would actually cover it because we have this z as the set of all integers when we go through there. Yeah, that's the reason we have to have that. We can't just say plus or minus 0.886 plus pi n. We need all the rest of them on there. Take a look at C. Cosine of x, 1.77. Anybody have any thoughts before we punch it in? Why not? Is a cosine between -1 and 1? Never going to be 1.77. That's undefined. Can't do it. No solution. Now, you would also see it if you graphed it. You'd go, wait a minute, these two are never hitting each other. This isn't never going to happen. So you could get it that way as well. So, let's see. Yeah, the one last thing we have to do is not graphing calculator oriented. So, set your graphing calculator off to the side. This is a little substitution and then a little trig to see what we can get here. And it says make the suggested trigonometric substitution and then use the Pythagorean identities to write the resulting function as a multiple of a basic trigonometric function. And it's been a while since you talked about this in algebra, but what I need you to remember is that if they give us the square root, it's called the principal root. That means they intended for us to always give a positive answer. The principal root means the book just wants to talk about the positive root. If they wanted you to see both, they would have put plus or minus in front of here. When we take the square root physically to solve, we have to use plus or minus. But the book said, we already did that, we're not interested in the negative one. We only want the positive. So here's what we're going to do. We're going to make x equal to this. And they're saying we're supposed to find something nice about that. Okay. Well, the first thing we would do is we would go ahead and square 3 secant theta. So it would be 9 secant squared theta minus 9. Wait a minute. We can factor 9 out of that. What is the square root of 9? 3. Secant squared theta minus 1. Isn't that what our Pythagorean identity? What is it? Tangent squared theta. Well, the square root of something squared is just the original, because square root and squaring, those are inverses of each other. But now we have to make sure that our answer comes out positive. Are there quadrants where tangent is negative? Of course there are. So we're going to have to put something on this problem that tells people no matter what you get, make it positive. What could we put on there? Absolute value bars. And the 3 is already positive, so it doesn't need them, but the tangent of theta, it's going to need them. You know, that's that principal root part. When they give us just the square root, that means they only want positive answers. All right, let's try this one then. Same thing, substitute it in. Looks much like the one we just did. So what are we taking out this time? Square root of 81, which is a 9. Tangent squared theta plus 1. That's another one I think we're supposed to know what that is. It is secant squared theta. Inverses again. And then what's the last step? Slap some absolute value bars on there. If you're one of the people that were looking at that going, well, I don't remember my Pythagorean identities. Remember, it's as easy as this. You write down sine squared theta plus cosine squared theta equals 1. And you think, what would I get if I divided everything by cosine? Sine over cosine, tangent squared theta plus 1, 1 over cosine, secant squared theta. And you have it. Or, if it's not going to be tangent or secant, you see cotangent or cosecant, go through and divide everything by sine squared theta. If you divide sine squared theta by sine squared theta, you get 1. Cosine over sine is going to be cotangent. And 1 over sine squared will be cosecant. Oops, that needs to be C. Right there. And it takes a matter of seconds for you to get those secondary Pythagorean identities that we have there. All right, that was all we had. But I know some of you had homework questions. So let me get a homework up here. You can get that written down. And then we'll just go as far as we can with homework questions.
Yeah.
We are out of here. Oh man, at 9:30.
You know, for this one, you put the equal signs all the way down. Well, that's what you did.
Oh.
You don't need to prove
No,
it.
there isn't.
Okay.
I was just thinking that make it look a little nicer. I could